Okay, guys, so we'll get started. Greg tells us that we have a question off the bat, so let's get started with that. Greg, what is that question? Greg, you'll have to unmute yourself.
Yes, I do have to unmute myself.
Okay, Greg.
Okay, I'm here now.
Hopefully you and I are the only people that are unmuted, so we don't have any other background noise. Okay,
Great.
shoot,
Well,
Greg.
okay, so this is from Alan N7, and the question is, what tells us that dark matter is not just unseen black holes?
That's a good question. Certainly, black holes are dark, so they are a form of dark matter. But we do have the ability to serve in the surveying of the universe, and these surveys have gotten more and more sophisticated over time, as we'll see. Astronomers have a pretty good idea of how much mass there is in black holes, and it turns out it's woefully not enough. If you think about, for example, the Nobel Prize of last week, where we, those two astronomers got the Nobel Prize for getting the details on the black hole in the center of our galaxy. Certainly, it's very, very heavy. I think it's 40 or 70 or something, I don't know, million solar masses, but clearly it's not the entire galaxy. So one could argue that there's not even as much dark matter, black hole mass, as there is visible mass, because they're all kind of embedded. Most of what we see is embedded in other galaxies. Whereas on the other hand, dark matter is about 5 times as much mass as all the mass that we know of made of regular atoms, including black holes. So black holes just isn't enough mass to account for that warping of space-time that we see caused by the gravitational lensing. That can only be created by much more mass, much distributed in a much different kind of way, and that is the conclusion that what we have here is the dark matter. Okay, so let's get started with today's class on dark energy. If you remember when we got started in the course, we gave a simple kind of quick definition of cosmology as being the study of the structure and processes of the universe and its evolution. And we said the game plan here for the course was to spend the first half of the course talking about the structure of the present universe, and kind of trying to inventory all the important elements in terms of cosmology that make the universe up. And then the second half of the course would be to look at its evolution, and that essentially is the model or the theory of the Big Bang. So today we want to finish up that first half to look at the last big important piece of the inventory that makes up the current the current universe as we understand it, and that's dark energy. But it turns out that there's another very important kind of energy that is also in the current universe, whose importance can't be overestimated in terms of the theory of the Big Bang and substantiating so much of that model, and that's the cosmic microwave background. And it turns out that we really need to understand something of the cosmic microwave background now to put dark energy into its proper context. The great discovery that we're going to talk about today is the fact that the universe is not only is it expanding, but that expansion is accelerating. The expansion is actually getting faster and faster. A great surprise that was discovered in 1998. And that's where this presentation is heading. But that by itself does not explain why astronomers and astrophysicists have to posit this enormous amount of new energy that can't be detected in any direct way, called dark energy. Just that expansion alone will not explain why this dark energy has to be hypothesized like this. We need to also understand something of the geometry of the universe overall. And that's why we need to introduce now, in a very natural way, the cosmic microwave background. It can't be introduced any prematurely in any way because of its tremendous importance. But my point is, we do have a few separate kind of dots for a while in this presentation before I can pull it all together at the end to explain in proper context where this incredible dark energy comes from and the role that it plays. So I ask you to bear with me as we go through the presentation. It's certainly dense. It's probably the densest presentation that I've made so far. We may not get through it all today because I don't want to rush it. There's no need to rush here in our call program. There's plenty of time to finish what I want to get through in terms of going through the theory of the Big Bang. So, but we do have a rather dense presentation here with a number of different ideas, a number of different threads before, like, hopefully I can convince you that it is all pulled together and the final understanding of where dark energy sits and the structure and processes of the universe. Okay, we'll start going back to Hubble's great discovery of the expanding universe. And here's a modern graph of the Hubble constant as we understand it today. It's about 70, its value, the h value for the law. The speed is equal to h times the distance. The speed of a receding galaxy is proportional to how far away it is. And that rate of expansion, that how the speed changes with distance, is best measured now to be about 70 kilometers per second for every million parsecs. That's a mouthful. What it means is if I'm looking at a galaxy at a certain distance and I see a certain speed that it's moving away from us by measuring the redshift, if I find another galaxy a million parsecs away from that, further away than the first one, it'll be going 70 kilometers per second faster than the first one. Whatever that first speed was, the second galaxy, I ask whoever that is to check and please mute yourself so that your noise, whatever noise you want to make is fine, but please mute yourself so it doesn't filter into the class. So if you were looking at that second galaxy, which is a million parsecs away, about 3.2 million light years away, it will be going faster because of Hubble's law, and it will be going 70 kilometers per second faster than the first one. That's what that means. Well, if you look at h, that is the value of the Hubble constant, we look at it just in terms of its units, 70 kilometers per second per milliparsec. The units are distance over time, that's the speed per distance. And we can simplify that by dividing by distance is the same as multiplying by 1 over distance. And notice we've got a distance in the top and the bottom, the numerator and the denominator, which will cancel. And so the actual units of this Hubble constant is 1 over a time. So therefore, 1 over the Hubble constant is a time value. It's in units of time, 1 over this 70 kilometers per second per milliparsec. We're going to ask, well, what time is that? Is it a significant physical number that means something? And in fact, it does. Let's assume that h is in fact constant throughout the life of the universe. We know in fact it's not. This is the great discovery that we're going to talk about today. But it is more or less constant. It doesn't change by twice as great as before. The changes are relatively subtle. So in the approximation, we can think that h is approximately constant throughout the life of the universe. And suppose let's take a galaxy which is certain far away, certain distance d, not too far away, so the velocity is not going to change all that much over time. And if we do have this notion that the universe started with a Big Bang, or even more simple, the point that we're at here is just starts from a very dense, small place, and it's expanding, as Hubble showed, so that you could run the clock backwards, and over the time of the universe, the length of the universe, it would have collapsed back to this beginning hot, initial, small volume. But yet now we see it at this distance d away. So what would d be? Well, it would be the speed that it would be moving at times the length of the universe. That's how far everything has been moving away from each other from that initial, what we now call the Big Bang. But we'll just think about it as a small, very hot, dense volume where everything is crammed together and the expansion has started from there. So the expansions are going on for capital T, the age of the universe, and how far that distance of that galaxy would be from us would be the velocity times the time, our good old third grade formula. So T is the age of the universe. Well, let's solve for T. T is then equal to the distance over the volume, approximately the velocity, the distance over the velocity. But according to Hubble's law, the velocity, the speed is hd. That's Hubble's law. So we have a d on top and bottom, and sure enough, what we wind up with is 1 over h. That's the time. 1 over h is a very good measure of how old the universe is, how long this is expansion going on. Again, if we can assume that the expansion has been more or less even and constant. Well, if you do that calculation for 70 kilometers per second per megaparsec, if you punch all the buttons right and get all the units smoothed out, what you'll find is that you'll get, indeed, a time in years to be about 13.8 billion years. Now, the actual computation to do this using a more careful argument, using the laws of general relativity, amazingly come up with very much the same number as this real back of the envelope kind of calculation. And this is the accepted age of the universe today, given our best understanding of the theory of the Big Bang. So this is a number which I start our presentation with because it'll become relevant, that we have some notion of how long this expansion that Hubble has identified back in 1929, how long this has been going on, if we can assume Hubble's law is operative and it's been happening since, the beginning of some very early, the early period where everything was kind of all more or less squashed together. Now we need to turn our attention, once having that fact, let's turn our attention to the geometry of the universe. Now, the geometry of the universe, you can imagine, is very, very complicated. We know that general relativity uses the very fancy non-Euclidean Riemannian geometry. We saw that last week in calculating what the kind of density distribution of dark matter is by looking exactly at that warping of space-time, calculating what kind of warping, what kind of Riemannian metrics are different in different places, depending upon the kind of gravitational lensing that we see. So yes, the geometry of the universe is very much non-Euclidean in its different areas, as certainly shown by what a galaxy, or more importantly, a galaxy cluster can do to space-time. But this question here for cosmology is, overall, given the universe, it's written wide, can we make some statement about the overall type of geometry of the universe? And it turns out that general relativity says, yes, you can. When you look at the universe writ large, there are 3 basic fundamental kinds of geometries that would be possible. One is called a positive curvature, which is depicted here, kind of a 2-dimensional idea of it, of the surface of a sphere. The real curvature of the universe is 4-dimensional of space-time, time being the 4th dimension. Here we're using a 2-dimensional model, so we can at least have some visual understanding. But the point is that you can measure that positive curvature if you could construct a very, very big triangle in the sky, in the universe, and measure the angles. If the curvature was positive, then you would find that the angles of that triangle would be, in fact, greater than 180 degrees. You'll see in your presentation, guys, I had 360 along the top, those numbers. I apologize, I caught that last night as I was going through the presentation, just for this morning. So please, if you want to change that, that 360, no, the angles of a triangle are 180, not 360. If the overall curvature had another possibility, which we call negative curvature, again in this Riemannian kind of space, then that big enormous triangle, if you could measure the angles accurately, you would see that they would be less than 180. And finally, if we had our good old Euclidean geometry, which astronomers call the flat universe, again, the overall general geometry of the universe writ large. If we had our good old 180-degree triangle, then that would give us what we call a flat space, and with basically zero curvature. And Einstein realized all this, and the early theoreticians who did tackle Einstein's equations, we'll mention at least one in a minute, understood this and realized this was lurking in his equations, that this is the kind of overall geometry that the general relativity could expect. And very importantly, what determines what geometry we have is, of course, the amount of matter in the universe. Just as the amount of matter and the amount of dark matter will create that kind of warping, the overall density of matter and energy in the universe will determine what kind of overall geometry we have, positive, negative, or flat. So not surprising, this is just, looking at it from the widest scale of the entire universe. So given these three types of geometries, again, Einstein's equations will suggest that there's a that the universe is not static, that is in fact either expanding or contracting. You can deduce this from the equations. We'll see Einstein was not happy with this, but it is a valid deduction from Einstein's general relativity equations. And if the universe had an overall positive curvature, then that means that there will be a lot of mass in the universe, and gravity eventually would take that expanding universe and begin to contract it back, and everything would fall back to that dense spot. And gravity would just overwhelm the natural expansion from general relativity, and gravity would bring everything back together. Notice that Newton worried about the very same thing when he posited his universal gravitation. That this would be a possibility, that the universe was not static as Newton thought, that this was a very likely scenario, that eventually gravity would win and begin to bring everything back. And this worried Newton about his notion of universal gravitation. If we had a negative curvature, well, that means that there wouldn't be as much mass to overwhelm the expansion, and the expansion would just simply continue on forever. Okay, just bigger. The universe would just get bigger and bigger and bigger, and the amount of gravity in the universe was not powerful enough to slow that down, to stop it, and certainly reverse it. Not at all. It would just completely expand forever if the geometry was so-called negative. Of course, it would mean that there wouldn't be enough mass overall in the universe to prevent this kind of expansion from continuing. And then the flat geometry. If the universe turned out to be flat, then we would have a very special. Again, general relativity predicted that there will be a very special kind of expansion. Yes, the universe would be expanding. It would be getting bigger and bigger. But that bigger and bigger will be getting slower and slower. The expansion would be getting slower and slower and slower. If the density, particularly the mass density, now we realize it's the mass energy density, but back in 1915, 1916, most of the mass of the universe was thought to, most of the energy of the universe was thought to be in its mass, because of E is equal to mc squared. That mass has tremendous amounts of energy in it. And if the density of the universe was just this funny, on a knife edge kind of value, then you would get this very special kind of expansion. That the universe would be expanding, but the expanding would be slower and slower and slower. We need to define some numbers so we can have a vocabulary about this. We talk about the density of the mass energy of the entire universe. The density of anything is very simple. It's the amount of that stuff, or whatever it is, divided by the volume that it's in. So the density of weight, the most common idea of density is how much weight there is divided by how big it is, the volume that it encompasses. The mass energy of the universe is exactly that. Take a survey, try to figure out how much the total mass energy that's contained in the universe, have the size of what the universe is, divide those two numbers, and that's the mass energy density of the universe. This is a measured number. You need to take a survey of how much mass and energy there is in the universe, get that as a quantitative number. You have to figure out how big the universe is, and you can do the division. General relativity formulas will compute this critical density. That is that density that you need so you get that special kind of third expansion. And it's interesting when you look at the formula, because we would have no ability to derive this formula. These are formulas from general relativity, you can imagine, are very, very complicated where they come from. But it's interesting when you look at the final result. The Hubble constant is in the numerator of the value of the critical density. Makes sense, right? The faster the expansion of the universe, the more mass you would need, the higher density you would need in order to have this very special kind of expansion that will be getting slower and slower. And the gravitational constant is in the denominator, which is a measure of the amount of mass. So depending on how large G would be, the measure of the amount of mass, well, then the critical density would not have to be so big. So it's interesting to see, just at a very, very high level, the expansion of the universe is in the numerator. The bigger the expansion, the higher the critical density needs to be. The greater the presence of mass is in the universe, in the denominator, that makes the fraction smaller, the lower the critical density would have to be. And the critical density, again, is a computed number, not a measured number. It's a computed number from theory, okay, in the theory of general relativity. And finally, we have omega, which is called the density parameter. That's mostly what we'll be talking about. It's the measured density over the critical density. Okay? It's a fraction. And if that fraction is greater than 1, that is, the measured density is greater than the critical density, that's all it means. When a fraction is greater than 1, it simply means the numerator is bigger than the denominator. So if the density parameter is greater than 1, that means that the measured density is greater than the critical density, and you will get that eventual collapse. If omega is less than 1, that means the measured density is less than the critical density. There's less mass than what you would need for that. Well, then the expansion would just continue on. There would be nothing to really slow it down. The expansion would be eternal, assuming that we're not making any more mass and energy anymore. Matter of fact, the density is getting smaller because the volume is increasing all the time. And finally, if by some strange coincidence omega was equal to 1, kind of this value balancing on a knife edge, that the measured density, this incredibly complex number that we would have to measure all these different things and come up with a value, if that was the same as the theoretical number involving H and G, then you would get this kind of very special expansion. The universe would be expanding, but the expanding would be getting slower and slower. Mathematically, it would be asymptotically approaching 0. That is, finally, the expansion finally would stop at infinite time. Okay? A mathematical statement coming out of the theory. You can imagine the expansion getting slower and slower. So if you were to wait to infinity, it finally would come to a stop. So these were the 3 choices that the theorists had figured out would be possible, looking at the deriving from the equations of general relativity. Well, Einstein was having none of this. He didn't like any of these expansions. Yes, he saw that from his equations, yes, that it did imply that the universe was changing. It was either expanding or contracting. And what he worried about was the contracting scenario, the same scenario that Newton worried about, that eventually the gravity of the mass of the universe would finally slow this expansion down and actually begin to reverse it and bring it back. This was not something that Einstein had any philosophical belief could possibly be. He was still from the school, as most scientists of his day in 1915 were, going back all the way in the tradition of science, that the universe was essentially static. Okay? This idea was still very, very firmly held in 1915, despite his new theory and what his equations said. And he worried about this scenario, just as Newton did. Remember how Newton solved it? He solved it by having God coming in every once in a while and tinkering uh, with the elements of the universe to keep everything more or less static, because Newton had no idea of an expanding universe in any way. Einstein wanted to do the same thing. He felt that something had to be done to stop this most likely scenario, that the expansion would be slowing down at some point and actually go in reverse. And here's his one of his summary equations to summarize the equations of general relativity. We obviously don't need to worry about the details of it, but it does have two sides of an equation. The left-hand side is the space-time curvature element of general relativity, and the right-hand side is the mass energy side. And remember, space-time tells matter how to move, and matter tells space-time how to curve. And it's all summarized there in the balancing of those two pieces of the equation. Okay? It's easy to remember that where the right side is the mass energy, the G, the gravitational constant, is the dead giveaway. Right? That's the mass energy side of the equation. And that fancy stuff on the left is all the Riemannian geometry metrics, which determine from the mass what the geometry will be. Well, you can see in this equation that, well, I'm sorry, what Einstein could see in this equation that there was a problem. And so what he did was he introduced the famous cosmological constant. He introduced a new term on the space-time curvature side of the equation, making it a property of space-time to keep the universe static, because he rejected this most likely scenario, and certainly the other two. He wanted the universe to be static, as 99% of all other physical scientists wanted it to be from, from the scientific revolution and even before. So he introduced this, what he called the cosmological constant. It's a fudge factor. He threw it in order to prevent his equations from predicting these kinds of expansions. He wasn't happy about it, but it mathematically solved the problem. And that's where the theory stayed for a while, at least in his view. I mentioned that there was other theorists who were working on these equations, making predictions from the general relativity. This is probably the most important one, Alexander Friedman, a Russian scientist. And he also saw that the universe should be expanding. He did not reject it. He felt that this is what the equation was saying, and the theory is true. And certainly the theories seem to be true, right? There's the perihelion of Mercury motion. There's the great experiments of 1919 of Eddington. General relativity seemed to be true. So, and this equation here is a famous Friedman equation, which measures the expansion of the universe. And notice that he was not afraid to use the cosmological constant in his work. This equation is very famous. It is still used today. It is really the starting point of all of the models of cosmology, certainly all the models of the Big Bang. Again, we don't need to worry about the details of the equation. I just wanted to show you the cosmological constant still could be used, but it wasn't necessary to have the expansion or the contraction. That seemed to come out naturally without the cosmological constant. That's why Einstein put it in. Okay. So the next part of the story is the astronomer George Lemaitre. He was a Catholic priest, but a recognized and well-known astronomer. He also looked at the equations. He also looked at Einstein's work and Friedman's work. He also looked very carefully at Slipher's data of the expanding universe, where Hubble got that from, right? All of the galaxies that Slipher measured with the redshift, the further away they were, the faster they were going. He looked at all of that, and he made the conclusion from all the analysis that yes, if the universe is expanding, it makes sense if you run time backwards that where this expanding universe that we have in front of us is must have come from some place where everything was closer together, very, very close together, depending on how far back you want to run time. To eventually there was a place where all the matter and energy of the universe was kind of in one very, very small volume of, of incredible density, of incredible temperature, incredible concentration of matter and energy. He called this the primeval atom, and this is really the beginning of the notion of the Big Bang. He did not flush this out in any great detail. Einstein completely rejected it when Lemaitre threw it out in 1927. Einstein famously said to him, "Your mathematics is correct, but your physics is atrocious." And he rejected this. I think Eddington rejected this idea. It was just a very radical idea that you have to accept the fact that the universe is inherently changing. But yet, of course, 2 years later, Hubble comes along with his data of all the redshifts, looking at that beautiful straight line linear relationship. And yes, Einstein had to agree. There was, in fact, the universe was, in fact, expanding. And this idea of running time backwards is not crazy at all. That's what that's what science is. That these laws work not only in the present, they predict the future. They also, of course, can predict the past if the law is operative over the whole time of the universe. So this idea, yes, began to develop real currency. This idea that the universe started from some kind of of what we now call Big Bang, and that was not then called that. Just the idea, the theory was not flushed out in any kind of elaborate way by Lemaitre. That there was this small, dense ball that the expansion started from, in some vague way. So when we look at these possible expansions now, the static universe is gone. We do have an expansion, and here are our three possibilities. And remember, those possibilities are created by ultimately by the amount of matter and energy in the universe will determine these expansions, because these expansions are ultimately determined by the overall geometry of the universe. And here down the bottom is just another way of thinking about these expansions, okay? So the actual expansion will be determined by the value of omega, the actual density over the critical density. And here you have the various values of omega, okay? So here would be that expansion ending and coming back, the size of the radius of the universe would come back to what sometimes called the big crunch, would look like this. Here is that very special expansion where it would asymptotically get slower and slower, approaching some maximum radius, and it would hit that maximum radius at an infinite amount of time. It was increasing. This line is getting higher and higher, but it's never going to go above this asymptotic line. The rate of expansion is getting slower and slower. That's the omega of 1. An unlikely value, you would think, given the fact that omega can be any value from 0 to infinity. Why would it have exactly the value 1? Physically, it would be, you would think, a very low probability of having exactly that value, unless there was some theoretical reason why, which could not be seen, certainly at the time. And this is where the matter is less than the critical density, and we would have that open universe where the expansion would just continue to coast. Okay, the last part, notice what I'm doing is we're going through the early history of the Big Bang model. Okay, so this will hold us in good stead, but we will end that history of the Big Bang model here with George Gamow. In the late 40s and early 50s, he and his graduate students, Ralph Alpher and Robert Herman, he set these two graduate students to study this basic idea. His basic idea is that if you think about, as the universe, rewind back time, think about that. What would it look like? What would the universe look like as it was very, very hot, very, very dense, tremendous ball of mass and energy, E is equal to mc squared, and the equivalency going back and forth in any way you like. What would it look like at that time? And it was well known in the late 40s and early 50s that it would be what we now call, what they called even at the time, a plasma. A plasma is basically where the matter is so hot, the energy is so high that atoms can't form, that the only thing that you can have are just nuclei of atoms. All the electrons are stripped away. And in the early universe, what his graduate students set out doing computations using quantum mechanics in the late 40s and early 50s, what they realized was what this plasma would look like would just be protons, deuterium nuclei, that is one proton and one neutron, and helium nuclei, two protons and two neutrons. These would be the only stable elements of the plasma in terms of neutrons and protons. And the electrons would be floating around all free, not being attached to any atom. No atom could form. It's just too hot. Okay? All these atoms would be ionized instantly if they ever tried to form because of the tremendous energy of the plasma. And so they looked at this. Plasma was being studied by the particle accelerators of the time. Properties of the plasma were being understood. And so they began to think about, well, what would come from this plasma as it began to expand, right? Because the universe is always expanding. Well, it would cool, okay? And eventually it would get down to a certain temperature that they could compute, knowing the properties of plasma, that if this temperature, when it got down to 3,000 degrees Kelvin, which is not all that hot in astronomy, as we'll see, then finally the plasma would melt away and atoms would be able to form. And that event, when that happened, as the universe expanded, it would inevitably get cooler. When it finally did get down to about 3,000 degrees Kelvin, the era that it's called is called the era of recombination. It's a terrible word because it should be called the era of combination. It's the first time atoms formed, but we're stuck. It's called recombination, and that's what it's called. We can't change it now. And if this plasma was formed some point back in the beginning, who knows what happened before the plasma was formed, but if the plasma was there at some time, a minute, 2 minutes, whatever, something insignificant in terms of the scope of time, insignificant in the scope of that 13.8 billion years, which was understood by Gamow and his staff, okay, that how long would it take to go from the beginning of that plasma, the formation of that plasma, to the 3,000 degrees. And they could do that computation, again, using the laws of quantum mechanics. This was all very well-known physics at the time. And they found it to be about 400,000 years it would take to cool from that beginning hot plasma state where the plasma would form down to the 3,000 degrees. And so this we would then, after about 4,000 years of the life of the universe, we would enter this recombination era. And here's a depiction of it up here, that the plasma finally would cool by its expansion, and finally the nuclei could trap the electrons, and we would have stable atoms. And a very interesting thing happens again then here. Again, well-known physics, that once you have, well, we start back with the plasma. In the plasma, not only do you have protons, neutrons, combinations of those as nuclei, like deuterium and helium, not only do you have free electrons, not only bouncing all over the place, not only do you have neutrinos, and all these things are all disassociated because of the tremendous energy, you also have light, you also have radiation, you also have photons. Well, the photons can't leave the plasma because whenever they start to move, they will inevitably bang into an electron. That electron will absorb that photon, go up to a higher energy state, release the energy with another photon, and the photons cannot make any progress at all. One of the well-known properties of a plasma. Light cannot exit from the interior of a plasma. It just can't get out. The analogy that's often made, which we'll see in a minute, is a cloud, cloud up in the sky, a fog. You can't see into the fog. The reason is because no light leaves the fog. You can't see inside it because no light is coming out from the inside. The water droplets of the fog or the cloud are blocking the light from coming out. Same thing, property of the plasma. No light can pass through the plasma. It's all just one volume. It's all bouncing around inside, and then the photons are not making any progress in the plasma. Once the plasma cools and we have recombination and we have normal standard stable atoms, again, most of these atoms would be hydrogen and helium, a little bit of lithium, but nothing to speak of. 99.999% of the atoms would be hydrogen and helium at this point, coming from the formation of the plasma. Light is finally able to move through that normal matter. And for the first time, light would begin to pass through into the volume of the universe. That phenomenon is called decoupling, the idea that the photons decouple from the matter and is able to move freely. All this, again, I emphasize, is known physics at the time. This was not some kind of wild speculation. By the time the graduate students, Alpha and Herman, were working on the details of this in the early 50s, this was all quite well known. So now that this light, these photons are able to move, this is light being given off at a temperature of 3,000 degrees. That's finally when the decoupling happens at 3,000 degrees. There will be light of 3,000 degree temperature. That's a certain spectrum of light, certain set of colors, a certain set of brightnesses glow when something is 3,000 degrees. Okay? And that light will begin to move out into the universe. And it's been moving out since the beginning of this decoupling era, just about 4,000 years, 400,000 years after the beginning of whatever the beginning of the universe was. And 400,000 years is nothing compared to the 13.8 billion years of the age of the universe. Again, I go back to that computation that was known at the time. And so the beginning of the very, very early universe, at some point very early on, 400,000 years is very early on, light finally, these photons of a temperature of 3,000 degrees, finally was able to flood the universe. Well, now, 13.8 billion years later, 13.8 billion years of expansion of the universe, that light is no longer at 3,000 degrees. Okay? Herman and Alpha were able to calculate that their calculation at the time in the early 50s would be about 5 degrees Kelvin. Now that would have been stretched, redshifted, cooled, brought down to a lower energy, and they figured it would be about 5 degrees Kelvin. Modern number now, when it was looked at again in the 60s, is more like 3 degrees Kelvin. The point is that it should exist. If you could measure a photon, if you measure a radiation of only 3 degrees Kelvin, which is saying something, that's a very, very low energy, right? 3 degrees above absolute zero. Okay, if you could measure that, then you could measure this light that was coming from the beginning of the universe. Interesting enough, no one tried because there just was not the technology back in the 50s to have this kind of sensitivity. There was just too much background noise of everything else going on in the universe, the stars, galaxies, raining down the sun, the most important energy source, raining down its energy and its radiation, that to detect something of such a small, weak signal was just not thought to be feasible. But this is where the theory of the Big Bang, we're going to let this sit for now, and that we do have this beginning egg over mantra that Gamow and his graduate students, who all became very important professors in their own right, developed this theory to the idea of the plasma and the cooling of the plasma, and coming to the area of recombination and decoupling. And therefore, for the first time, this primeval egg kind of theory has something that makes a prediction. And that's what theories need. If you want to test a theory, you need to make a prediction. That's what Einstein was able to do with the precession of the perihelion of Mercury. He made a prediction. He made a prediction of what the number should be compared to its measurement. And of course, most famously, he made a prediction that the light would be bent by the rim of the mass of the sun. Okay, and that was then established by Eddington. Finally, here, what Gamow and his staff was able to do is to make a prediction that there would be this radiation still flooding the universe today. Whether it was detectable or not was another story. Again, Eddington had a very tough time detecting the bending of light. Having to wait for the solar eclipse and taking all these measurements and doing all this analysis. So yeah, technology sometimes has to catch up with you in order to test a prediction. But the first thing you have to do is be able to make a testable prediction, at least in theory. And this is what Gamow was able to do. Again, the picture that as the universe expands, the light, the photons are also expanding. They're also being stretched as it travels through time. So the spectrum of the light would not look like a 3000 degree Kelvin spectrum. And if you're not sure what I'm talking about there, I will go into a bit more detail in a moment, but you need to understand the idea of spectrum. The spectrum wouldn't look like a 3000 degree body. It would look now stretched to be something far, far cooler of only just 3 degrees. Okay, so talking about light. A review, when I talk about light, talk about radiation, I'm talking about the entire spectrum of electromagnetic radiation. Okay. Before we continue on, I'm at a natural stopping point because we finished kind of the beginning story of the Big Bang, as it turns out. Greg, do we have any questions outstanding?
We have one comment and a question.
Great.
Alan in 7 says, but I thought current measures of expansion indicate an increasing rate of expansion.
You are dead right. That's the whole point of this presentation. If you go ahead and look at the last 4 slides, that's what I'm showing.
Okay, and we have a question from Sharon Beatty. What are the units of the mass energy density? I am having difficulty making the units work out looking at the critical density formula.
Right, right. Yeah, you're not going to get it from that formula. Those formulas of general relativity are very advanced, and you're not going to easily get it from there. Think about the simplest density we have, the density of just weight, of mass. Think, hold a ball of aluminum in your hand, hold a ball of iron in your hand. The iron is much more dense. If the 2 balls are the same size, the reason why the iron, we call it more dense, is because it has a much greater mass in the same volume. That's all density is. It's simply a measure of the amount of stuff that you're talking about in the volume that is contained in it. Come now to the mass energy density. We need to calculate the entire mass of the universe, which is not easy, the entire energy that's contained in the universe, which is even harder. Get that one number, that would be the numerator number of how you would compute that, and divide that by the size of the universe, okay? By the volume of the universe. That number is the mass energy density of the universe. You can imagine, first of all, it's a measured number. It's a number that astronomers have to go out and take samples of larger and larger pieces of the universe, gathering up how much mass is there, gathering up how much energy they can see there, and coming up with a number in the numerator, knowing what volume they're looking at, calculating the volume there, and getting a sample of what the energy density is for that particular survey. You do that again and again, all kinds of places in the universe, bigger and bigger surveys, more and more sophisticated surveys, using more and more powerful telescopes, ultimately ending in the Sloan survey, which we'll be talking about next week, the ultimate gold standard of these kinds of surveys. And you come up with a measured number of the density of the matter density of the universe. It's amazing that we can do that. You take that number in the numerator and you divide it by the theoretical number that relativity insists upon having if you want that critical kind of beautiful expansion, slower and slower. If that's what you want, this is the kind of density that you need. You put one number over the other and you get a measure of how close you are to the critical density. You can be above it, you can be below it, or you can, for some reason, that measured number can hit dead on the theoretical number that would give you that flat universe. Okay? It's a long shot, you would think, to hit that number, but that's really all that density parameter is. It's simply a fraction of what the measured density is over the theoretical density to get that special kind of geometry. Okay, so the electromagnetic spectrum, we've all seen this picture before. We realize that light, visible light, is a very small piece of the entire range of what these light waves can be in terms of what their frequency or what their wavelength can be. Okay? Remember, the wavelengths of light go in measured in nanometers, billionths of a meter. The highest frequency, the shortest wavelengths is in the 400 nanometer range for the violet, the longest being 700 meters. But if you look at that scale above that, you can see that we go from AM radio waves, which is 100 meters, right? From crest to crest of a radio wave is the length of a football field. Okay? And the wavelengths get smaller and smaller and smaller, going up into the various different bands, from FM and TV and radar to the infrared light, which again we can't see, but some animals and insects can see. So we get our visible range, and then we get even beyond that, the ultraviolet, the X-rays, even of a smaller, shorter wavelength, till finally we get to the gamma rays. This is all the same physics. This is all the same physical entity in the universe. The only difference is it has different wavelengths. Associated with them is different frequencies, different energies. Okay? And the higher the frequency, the shorter the wavelength, the greater pound for pound the energy. So gamma rays is the most energetic. The radio waves would be the least energy. So that's when we're talking about light, when I talk about light or radiation, remember I'm talking about this entire spectrum. And astronomers have looked at the sky, looked at the universe in all these different wavelengths to gather information of different kinds. And we'll see examples of this as we go along. We already saw this with the study of dark matter. Remember that hot gas that was giving off X-ray light. And from the X-ray light, we could measure the temperature of the light, measure the spectrum of the light, therefore measure the temperature of the gas, and know, wait, how can this incredibly fast gas be contained in the matter that we see out there? It can't. There must be much more matter out there to contain that very, very hot, very fast moving gas, okay, so that it does not dissipate. So we're already looking at different parts of the spectrum when we're looking at the X-ray emission of very, very hot gas. We'll see in a moment that the cosmic microwave background is in the lower infrared range because of that very cool 3-degree temperature. Okay. We have all these scales here from nanometers all the way down to meters. I just wanted to point out where a micron is. A micron is a millionth of a meter. And it sits right there at 1,000 nanometers, right? 1,000 billionths is a million. And so that's where the micron is. We'll be talking about microns. So I just wanted to show you where 1 micron was. 1 millionth of a meter is 1,000 billionths of a meter. Okay, so let's talk about spectra, what we need to know here in this context. We know that hot things glow. We have things which are red hot. When they get even hotter, they become yellow hot. And we have the phrase, literally it's true, that something gets so hot that it is white hot. We know that white is not a color, right? We know that white is all the colors of the rainbow, okay? So when you look at that yellow, that is not one color. There is a spectrum of colors being given out. Our brain processes all those colors coming at us simultaneously at their various different brightnesses as that color yellow. The same for the red. That is not one color. Every hot body, every glowing body gives off a range of colors of varying different brightnesses. And they kind of look like this. Depending upon the temperature, notice things get hotter and hotter from 550 degrees centigrade all the way up to 1200 degrees centigrade. We go from the red hot to the white hot. Notice that here, and here is the spectrum. Here is the range of wavelengths that are being given out, okay, by something which is 550 degrees centigrade as opposed to something which is 1200 degrees centigrade. You'll notice a few things about these two spectra. One is that the hotter element gives off more wavelengths, gives off more colors than the cooler one does. It gives off more energy. The whole mountain is higher. The total amount of energy is higher, giving out at 1200 degrees as opposed to 550, which makes sense. And interestingly enough, the brightest wavelength, the wavelength that's coming out of the emission, which is the brightest one of all, is getting shorter and shorter, which makes sense as the energy, as the heat, is higher and higher. So these are very qualitative spectrum for us to remember that when you're looking at a color, what your brain is doing is synthesizing that in some way to get the color that you would call it, whether it was egg-shaped blue or killy green, okay? But when you're looking at something which is glowing, there's always a range of colors being given out, and they can be analyzed by a prism type device, a spectroscope. And these curves, these more detailed curves, were studied in great earnest at the turn of the century to try to understand what was going on that would create these kinds of spectra at these kinds of temperatures. So we have temperatures at 100 degrees Kelvin, 300 degrees Kelvin. Here's our 3000 degree Kelvin. Here is the range of wavelengths. Here are the range of colors that were given out at the time of decoupling. And some of it would be in the visible light. Notice that the brightest would be coming out would be red. Okay, but the brightest of all, the very peak, is not in the red, but it's actually in the infrared. But this would be the range of electromagnetic waves coming out at the time of decoupling. So it would be visible if there were any eyes to see, which there weren't any. Here's an important spectrum here of the 5,774, funny number. That's, depicting that's the temperature of the surface of the sun, okay? And so this is the spectrum that's being given out by our sun. Now, surprisingly, it peaks in the visible light. Yeah, our eyes have been adapted over evolution to use the brightest energy source that's coming from the sun. Not surprising, okay? Notice it peaks here in about the yellow-green area. But yet, there's ultraviolet light that's being given out by the sun. There's infrared light and radio waves that are being given out by the sun. But most of this harmful ultraviolet light isn't actually protected. We're protected by the layers of the atmosphere, that we don't get most of this. We get some of it. That's why you can get a sunburn on a cloudy day. And some of this infrared light is also blocked. Some of it goes through, some of it gets blocked, depending upon the wavelength and what's the water vapor and the carbon dioxide in the air, which is blocking it. The point is that these curves were greatly studied. Physicists wanted to be able to understand what was creating these exact curves for these different temperatures. The bodies giving off these kinds of light were called black bodies. We'll give a definition of what that is in a moment. But this was one of the great questions of the late 19th century, to understand these curves, to be able to predict them theoretically, so that when you knew the temperature, you would know exactly what the curve would look like. If I gave you a wavelength for a certain temperature, could you tell me just how bright the light was coming out from that wavelength? Another look at these black body radiation. What does this term black body mean? Well, an incandescent substance, something which is giving off its own light, like a light bulb, like the sun. If it has the property that it does not reflect any light, that the only light coming from it is coming from it internally, that it's in, fancy word, it's in thermal equilibrium with itself, then the light that would be giving out, the spectrum giving out, would be of this perfect theoretical form of the black body radiation. Turns out that you can produce a black body radiation very well by making a kiln of these various temperatures, a hot inside walls kiln of temperature of 3,000 degrees or 5,000 degrees. The light that glows out of that kiln is very, very close to theoretically of a black body. And that's the way they were studied back in the turn of the century. What's important for us to realize is that when you're looking at anything which is going at a temperature, you're not looking at one color, although our brain only sees one composite color. You're looking at a spectrum of colors. Here's again the spectrum of the sun, okay, peaking here in that green yellow zone, here about 6,000 degrees. What's important to realize, what the scientists at the turn of the century realized, was that the temperature determines the spectrum for a black body. If you just know the temperature, the spectrum, they had a catalog of these spectrum by taking detailed measurements for given temperatures, that the temperature totally determines the distribution of the colors among their various brightnesses in these kinds of curves. And for our purposes, you could reverse the other way. That from the spectrum, if you took these enough measurements and be able to build a curve, you could tell what the temperature of that body was that was glowing and giving off that spectrum. This will become central for us to understand. Okay? That the temperature and the spectrum, that the spectrum is a unique fingerprint for a black body glowing at that particular temperature. The Holy Grail was to find the theoretical formula that could make that connection, that could actually compute what the different brightnesses would be for the different colors, different wavelengths. Remember, when I say colors, I mean all kinds of colors: ultraviolet colors, gamma ray colors, infrared colors, not just colors that we can see, to be able to compute for any given temperature what the spectrum would look like, and therefore be able to go backwards. By looking at a theoretical spectrum, you could go ahead and tell the temperature. Stars, for example, are black bodies, very, very close to perfect black bodies. Here's again the spectrum of the sun. Here's a spectrum of a much hotter star, Spica, where the spectrum actually peaks in the ultraviolet. And here is a very cool star, Antares, or red giant. And notice that 3,400 degrees, very close to the 3,000 degree. Okay, it's a little bit hotter than the original cosmic microwave background, as it left decoupling, but it does peak in the infrared. Well, the person who was able to do that was Max Planck. He was able to finally find the theoretical formula that would connect the shape of the spectrum with the temperature. Okay, and it's a bear. It's one that we don't have to worry about, but just to look at the elements. This is the brightness. If you want to, given a certain temperature T, if you want to know the brightness of any wavelength, just put the wavelength into the formula. Do a big computation, okay? And what you will get is the brightness for that particular wavelength, okay? Keeping the temperature fixed. You will get all these different brightnesses, each different brightness for the temperature, for the wavelength that you put in. These are the only two variables in the formula. There's the wavelength and the temperature. All the other numbers are constants. We recognize the speed of light. We recognize h as Planck's constant. Of course, where did Planck come up with this formula? This is the beginning of quantum theory. Right? In order to come up with this formula, incredibly accurate formula, which predicts the black body curves precisely, is he had to make the assumption that the energy coming from the black body comes in packets or in quanta. And so the quantum theory was born. A totally different story. But I just wanted to point out that there is a formula that you can calculate the various brightnesses given the temperature and the wavelength. Or reverse the other way. If you know a whole bunch of wavelengths and what those energies are, that is, if you know the curve observationally, empirically, you can back out and see what temperature you keep calculating over and over again to see what the temperature of that spectrum represents. Another formula, which is a bit easier to handle, which was known before Planck's formula, was Wien's formula. Planck, by the way, won the Nobel Prize in 1918 for this formula, the beginning of the quantum theory. And Wien's formula, he got the Nobel Prize in 1911 for his. He asked the question, can we figure out a formula that will tell us what the brightest color is? What's the brightest wavelength that comes out of these temperatures? And it's a nice formula. It's very close to just 3,000 over the value of the temperature. Very easy to, if you want to know what the wavelength is of the brightest, the peak of the spectrum. You would measure the wavelength in microns. There's that microns again. And in all of astronomy, temperatures are always measured in Kelvin. So this is a nice little formula. We can have some fun with this formula. Let's just look at it for a minute. Let's take our favorite temperature, okay, 98.6. We'll take a temperature of 100 degrees Fahrenheit, which is about 330 degrees Kelvin, and let's apply Wien's formula, 3000 over the temperature. So the maximum temperature coming out of us as we glow, because we are a hot body, would be about 0.9 microns, almost 1 micron in the infrared. And here's an infrared camera. Okay, here's the warmest part of us, our skin. Okay, okay. The skin is being shielded by the shirt, so this is a cooler part. Our hair is cooler. Your hair is blocking the heat coming from our skull. And here is the eyeglasses, which is really blocking a lot of the infrared light that's coming out from that part of his body. So we have a hotter part of his body. Here in the shoulder is cooler part of his body because some of the infrared is being blocked by the shirt. And here is the range of temperatures coming from that. Okay, so we know that we glow. We know that as we go through the airport, being subjected to this kind of scrutiny, and these infrared cameras. What would James Bond movies do without them? And let's look at one more. Let's look at the sun once more, just for fun. Okay, the sun has a temperature of about 6,000 degrees Kelvin, and we know that it peaks in the visible part of the spectrum. It actually peaks in that yellow-green area. Let's check out the formula. Surface of the sun, 5,800 degrees Kelvin. Let's apply Wien's formula of 3,000 over that temperature, and you'll get 0.52. If you punch the buttons in the calculator, you'll get 0.52 microns, okay, or 520 nanometers. Indeed, the range of the yellow-green. Okay, so a nice formula, nice kind of rule of thumb to know when you're looking at a spectrum of a hot body, of a glowing body. You can kind of easily calculate what that peak would be, if that would be of interest, to get kind of a bearing as to what the spectrum is about. Okay, so in the last 5 minutes, before I start with looking for the Big Bang, let me stop and ask Greg if we have any questions outstanding.
Yes, we have one question. From Sharon Beatty: is the Doppler shift accounted for within Planck's constant?
No, the Doppler shift isn't about Planck's constant. These are fixed bodies which are glowing like the red bar, and you just look at this thing which is fixed, and it's giving out light of all different colors, and you measure them, and you measure the curves, and you try to get a prediction as to try to get a formula to predict that curve. There's nothing moving here, so we don't worry about red shifts and blue shifts. The source of the light is actually stationary. Okay, so let's finish up. I think we're going to come to kind of a natural place where we're going to stop here in 5 minutes. So that's good. And as I thought, we're not going to finish this presentation. We'll finish it next week. I think it'll take 2 presentations to get through this, but we still, as you can see, we've had a lot of ideas so far, and they seem to be disjointed. Like we kind of going from one topic to another. All of a sudden, we're in black body spectra. Why is this? Well, here's the reason why. Because finally, in the early 60s, someone took Gamo's idea seriously, and they thought the technology was ready to actually look for what's now been called the cosmic microwave background. And that was done by the Princeton astronomer, Robert Dicke. He also had a staff of junior people and graduate students. And Dicke, the work he did during World War II was in radio astronomy, and he actually designed a very sensitive radio telescope called the Dicke radiometer. And he had some of his junior staff start to build one of his radiometers of very, very exquisite sensitivity, as best they could as physicists, searching for this 3-degree temperature that should be glowing in the sky. They actually set out to try to find this. One of his graduate students, not an experimentalist, but a theorist, named Jim Pebbles, he set him to start thinking about, he said to Jesus, I want you to think about this radiation that we will be looking for. What properties should it have? What kinds of things should we be looking for? What could it tell us if we could find it? And Pebbles did that. He's the Nobel Prize winner of last year. It's one of his talks that I highly recommend that you watch, that he gave in the Nobel Prize lecture. Very, very illuminating talk. Not every detail will be understandable, but you will very much get the gist of what he's talking about. And to listen to these firsthand experiences, you just get a totally different view, guys, of what's going on compared to listening to me. What do I know? I know from what I read in books. Okay, you want to listen to the guy who actually did this work is just a wonderful opportunity. Pebbles is the one who brought the 5-degree Kelvin down to the 3-degree Kelvin, a much more accurate number. And again, let's look at Wien's formula. What are they looking for? What's the brightest signal that they will be looking for among the spectrum? Again, it'd be 3,000 over that 3 degrees, and it will be 1,000 microns, better known as 1 millimeter, better known as 1/10 of a centimeter. Really substantial. The length from crest to crest of the brightest thing coming out of the cosmic background would have a wavelength of 1 millimeter. Okay? That's light in the far infrared. So they began looking for. They were all set to start to look for this thing. And here's the spectrum that Pebbles came up with the refined temperature. Here's a more accurate one of temperature of 2.7 some odd. This measurement this is probably one of the most exquisite measurements ever made, been measured over and over and over again, the spectrum of the microwave cosmic background, as well as we'll see as we go through the theory of the Big Bang. So I'll end here. Just as these guys were building this thing, these theoreticians and college, university professors were doing this. A couple of radio astronomers at Bell Labs, I think 20 miles away, found the cosmic microwave background. This is a wonderful story. I know many of you have heard it, but some of you probably have not. This story needs to be told of just how this radiation was found by these two astronomers from Bell Labs. They were on the engineering side of things working with Bell Labs. They were not theoreticians. They have interesting backgrounds in themselves, and the actual story and the interaction between them and the Dickey group is a story of legend. Okay, and I don't want to rush it, and we're out of time, so we'll stop there. Greg, any final questions before we go?
No final questions.
Okay. Anybody have any thoughts? Anybody want to unmute themselves and ask a question before we go?
I am not an astronomer by any means, and I'm wondering if we ever answered the question as to what the shape of the universe is, or am I anticipating your further lectures on the Big Bang?
Well, in one sense, but no, in another sense, the shape of the universe from us is a sphere, right? We can look out basically in any direction we want. Some directions are blocked by the dust of the Milky Way, but we basically look out with the best telescopes that we have, the orbiting telescopes. And so what we can see, the visual universe, as it's called, the observational universe, would by definition be a sphere. Okay, how big that universe is, that's the question that I asked to put off at the time, and we certainly will be getting into that question. Okay.
I have a question. I have one question.
Yes, please.
Peter?
Yes.
Yes, so it's just a simple question. I wonder then, why do we call ultraviolet light and not ultraviolet spectra? Because I think when we are talking about light, it starts getting confusing, and I wonder if that's just a convention that we have, or is there another reason?
Well, no, it's ultraviolet because it's beyond the violet, just as the infrared is beyond the red. When you look at the spectrum again, if you go back to that spectrum picture that we had, and you just look at the position of what's called the ultraviolet light, it's just above the violet in wavelength, and the infrared is just longer, slightly longer than the red. And that's where these words come from, ultraviolet and infrared. So it's kind of a relative term.
Okay.
All right, guys, so that will be it. Have a good week, and I will close off and say goodbye.
Thank you.
Thank you.
Okay.
Peter.
Okay. Have a good week, guys.